Welcome. This video corresponds to Chapter 5 in the Brown SL Chemistry book, and it starts looking at energetics. And so in the first part of Section 1, we're going to talk specifically about energy changes. And a lot of this will be review from our first-year chemistry course, but just to help you remember all these different terms, I'm going to go through this fairly quickly, but try and be thorough. So all chemical changes involve a change in energy. Either energy is absorbed or energy is released. When it's absorbed, we call it endothermic, and when it's released, we call it exothermic. And the reason for this is that a chemical change involves breaking bonds and then making new bonds. And bond breaking is going to require energy or be endothermic, and bond making is going to be exothermic. And those two activities are not going to require the same amount of energy. So either there's going to be more energy for bond breaking or more energy for bond making. And the first law of thermodynamics says in chemical transformations, energy can neither be created nor destroyed. So if there's more energy needed for bond breaking, then it's going to be an endothermic reaction. But if there's more energy released in the bond making, it's going to be exothermic. So the natural direction of change is toward greater disorder. And this is an idea in science called entropy, that both energy and matter are going to be dispersed more whenever possible. So energy then is defined as the ability to do work, or in other words, to move an object against an opposing force. So forms of energy include heat, light, sound, electricity, and chemical energy. And chemical energy is often also called chemical potential energy because chemical energy is potential energy. It's stored in the bonds of the substance that you're studying. So heat is a mode of energy transfer. It's the result of temperature differences. It increases the disorder in how the particles behave and increases the average kinetic energy of those particles in a disordered fashion. So 1 joule is the common unit for energy and work, especially heat, and 1 joule is equal to 1 Newton of force moved over a distance of 1 meter. A couple other terms we use a lot in energetics is systems and surroundings. The system is the actual area you're interested in, what you're studying. So the specific reaction you're doing, whether it's in a test tube or a beaker or whatever, that's your system. And then the surroundings in theory is everything else in the universe. More specifically, we look at just, the environment around the reaction vessel that you're using. We can also describe systems as open or closed. An open system can exchange both energy and matter. So this is when you're heating something up in an open beaker and gas is free to leave and temperature also changes as you're doing that. In a closed system, energy can be exchanged but not matter. So regardless, energy can be exchanged between the systems and surroundings in any system or any reaction. Okay, so although the energy can be exchanged in either system, open or closed, total energy is conserved. Remember, that's the first law of thermodynamics. So we often study what's called enthalpy, which is the total heat content of a system. And that's just Greek for heat inside. And more specifically, we studied the change in enthalpy. We rarely can actually know what the total heat content of a system is, but we can pretty easily calculate the change in enthalpy. So enthalpy is represented, or I should actually say change in enthalpy is represented as delta H, with a positive value occurring when energy is transferred in, or it's endothermic, and then a negative value when energy is transferred out, or it's exothermic. A lot of times you hear about heat flow, and heat flow, it can be a good word to describe what's going on, but it's also misleading because energy can be transferred without any matter actually being transferred. Heat is just the transfer of energy. It's simply faster moving particles hitting slower moving particles. And so then the slower moving particles speed up, the faster moving particles slow down, and that's energy transfer or heat transfer. So the enthalpy of a system, or the heat of a system, the energy of a system is stored in its chemical bonds and in its intermolecular forces as potential energy. So if it's a gas, now the intermolecular forces are no longer at play and it's just going to be in the chemical bonds. When it's in a solid and a liquid form, then the intermolecular forces can become a big deal or a big part of this enthalpy. So this means both reactants and products have an enthalpy associated with them since they both have for sure chemical bonds and possibly intermolecular forces. And during a chemical change, an enthalpy change will occur, again, as bonds are broken and then new bonds are made. And again, these two processes will not require or release the same amount of energy, so there's going to be an energy transfer either into the system or out of the system. And that means the products will either have an increase in enthalpy or a decrease in enthalpy, which we call endothermic or exothermic. So let's look at exothermic reactions. Most reactions are exothermic, including almost all combustion reactions and all neutralization reactions. And exothermic means heat from the system is transferred to the surroundings. This means the products have less potential energy stored in their chemical bonds than the reactants did. And it means the bond breaking took less energy than the bond making. Okay, so the enthalpy change is considered a negative value. So I want to take a minute to look at this graphic here, because this is how I like to represent endothermic and exothermic reactions. So on the x-axis, I have time, or you can call it, the reaction over time. And then on the y-axis, I have potential energy. I just have it abbreviated as PE. I'm going to write in products here because that got lost in the translation. So you start out with your reactants, and your reactants have a certain amount of potential energy. So that's why this is just a straight line here. As long as nothing's happening to the reactions, the potential energy is going to remain constant. Then you always have to put energy in. We talk about activation energy. You have to put energy in to have this bond breaking occur. So this is always endothermic. It always requires energy. And then up here, this plateau, this is kind of where the magic happens. This is the transition state. It's where the reactant particles have been broken down into their constituent atoms. They're crashing into each other, and if the collisions are correct orientation, correct energy, then we make new products. So as new products are made, new bonds form, and that's along this side here then, and the bond making is always exothermic, so energy is released. And in this case, you can see the difference in energy among the reactants and the products has decreased by this much because the bond making took more energy than the bond breaking. The bond making released more energy than the bond breaking, and that's what I'm indicating here. Bond making is greater than the bond breaking enthalpy change. So heat is lost, and it's lost to the environment. The system loses it, the surroundings pick it up. So we would feel the heat being given off. So that means our products have less potential energy, and it also means they're more stable. That's why exothermic reactions are so common, because they lead to more stable products. So here's how your book represents it. They show you the graphic that when energy is coming in to the system, I've got these just reversed. This is my endothermic up here, and this is my exothermic down here. So let me just pull this up and let's look at the exothermic. So in an exothermic reaction, heat from the system is moving out into the surroundings. So you see up here, this is your reactants with their potential energy, or H, their enthalpy before, and after the products have less potential energy. So that shows me there's a decrease in energy or release of energy. Or here they've actually haven't marked reactants and products, and instead of time they call it the extent of the reaction. And then if I go back up here, the endothermic is just the opposite. Now we have energy coming into the system. So the reactants before have less energy, and the products after require more energy. So in this case, in the case of endothermic, it means the bond breaking is going to take more energy than the bond making. So there's a net transfer of energy into the system. And again, there aren't that many chemical reactions that are endothermic because it's not the natural direction of a reaction. So standard enthalpy changes. Since enthalpy change involves chemical bonds as well as intermolecular forces, the state of matter, or the conditions that the reaction takes place at, matters. It's a big deal if it's a solid, a liquid, or a gas. So often, enthalpy changes are measured under standard conditions, and it's called a standard enthalpy change. And this little symbol right here lets you know standard conditions were used. And standard conditions are a pressure of 100 kilopascals. That's about 1 atmosphere, so it's pretty close to what is typical air pressure around us. concentration of 1 molar for any solutions. Substances are in their standard states. That just means the state they would be in at 1 atmosphere and 1 molar, as well as at room temperature. And so temperature isn't technically given, but it's assumed to be 298 or room temperature because standard state means the normal state at room temperature. So it kind of is implied in the definition. So thermochemical equations then differ from just a regular balanced equation because they have a little more information. By definition, they have to include the state symbols and you have to include the enthalpy change for 1 mole of that product. So this will be expressed as kilojoules per mole, but if I look here, I've got 6, 6, 1, and 6. This is being expressed as kilojoules per mole of product of glucose being produced here. And just a quick word on temperature. Temperature is the average kinetic energy of the particles of the object, or the motion of the particles. So when temperature decreases, the average kinetic energy of the particles also decreases. That means 0 is really the lowest possible temperature. And Kelvin's the one who realized this, that if temperature is motion, then at 0 motion, it's 0 temperature, and there is no negative temperature. So that's why we use the Kelvin scale, because it's the only one where there is absolute 0. That's the bottom. There is no more. So heat is dependent on temperature, but it also depends on the mass of the object, the heat or energy being added or removed, the nature of the object, which is reflected in its specific heat capacity. And nature of the object has to do with its bonding, its size, its mass, a number of things. So heat change is abbreviated as Q, or you can use delta H. And it's calculated by what I like to call MCAT, mass times specific heat capacity times change in temperature. And the temperature change can be given in Celsius degrees or Kelvin. You don't have to change to Kelvin because you're going to use the difference in temperature. And 1 degree Celsius is the same amount of energy as 1 Kelvin. So if you change to Kelvin, subtracted them, and then converted back, you would have the exact same change in Celsius degrees. So in this case, it's okay to leave it in Celsius. And then one final thing, specific heat capacity is different than heat capacity. It's big C versus little c. This is kind of like kilocalories versus calories. In America, we just write it capital C calories and little c calories. Specific heat capacity is the little c. It's the heat needed to increase the temperature of a specific mass of a specific material. So that's why it's called specific heat capacity, because it's specific to a mass and a material. So metals tend to have low specific heat values. They heat up and cool down quickly, while nonmetals tend to have higher specific heats. They heat and cool slowly, or we call them insulators. And again, this is abbreviated with the lowercase c, and this is the value we use when we calculate MCAT. But there's also a thing called heat capacity, capital C, and that's the heat needed to increase an object by 1 Kelvin. So you calculate just for the object you're interested in. It only compares the change in heat divided by the change in temperature, so the unit's going to be joules per Kelvin instead of joules or kilojoules like specific heat capacity. And it allows you to quickly compare 2 objects regardless of the material or mass. If you're just wondering, you've got 2 objects side by side, you want to know which one has the better insulating qualities or the better conductivity qualities, you just heat them up and see. So a large lake has a greater heat capacity than a small pond, which is why a large lake is better at moderating temperature. It helps to keep the city near it cooler in the summer and warmer in the winter, whereas a small pond's not going to have much of an effect on that because of its smaller heat capacity. And heat capacity is abbreviated with the capital C.